Welcome, dear half-ass viewers. If you're new here, welcome. We're glad you're here. And if you're a returning viewer, welcome back. In our last episode, episode 4, we battled some serious challenges just getting the camshaft installed. After plenty of finagling, we finally got it in. Now in this episode, we're hunting for true top dead center to figure out which of the 2 timing marks on our mystery Chinese damper is actually correct. And just wait until you see what we discover. From there, we move on to degreeing the camshaft, but the numbers we're getting are all over the place. Nothing wants to cooperate. And if that weren't enough, we run into yet another hurdle, figuring out the right pushrod type and length. It's unbelievable. So yes, the struggles continue. Stick with us to see how, and if, we manage to sort out this latest round of problems. Before we get started, we just want to say thank you for being here. This channel has grown to 685 subscribers because people like you decided it was worth their time. We're only 315 people away from reaching 1,000, which is a goal for us. And if you'd like to stay with us and help us get there, we'd truly appreciate you hitting that subscribe button. Thanks again for being a part of our family. We've got the crank, rods and pistons in, and the camshaft is in, so now it's time to install the timing chain set and degree the cam. The next step is to degree the cam. I'll be honest, despite building many engines over the years without a single issue, we've never actually done this process before. And there are plenty of great videos out there explaining the how-to of the process, so we're not going to get into technical details here. You can find those videos on your own, but we will tell you why you should care. Given the fluctuating quality of modern parts, we were strongly encouraged to degree this cam, and it's a good thing we did. We purchased a timing chain set featuring multiple index positions specifically to dial everything in perfectly. However, when we started with the 0 offset position and measured the lift, the numbers didn't match the index marks on the crank pulley. Confused, we remeasured and got the same results. To make a long story not so long, we tried nearly every clocking position in this set. Even when we finally found a position that got us close, I still felt uneasy. So we called the supplier, TA Performance. Now they're not the manufacturer, they're the supplier. And we spent 45 minutes on the phone with a very helpful expert. And after reviewing our steps, he agreed we were doing everything right. The numbers just didn't make sense. Our conclusion? The parts were manufactured incorrectly. Had we simply lined up the dots and trusted the sprockets, we would have been screwed. The engine would have run terribly, and we would have been left scratching our heads as to why. So if you've never degreed a cam before, take it from us. With today's parts, you'd better start doing it. Now that we got the camshaft dialed in, we're applying some Loctite primer to the threads in the cam, as well as the bolt threads that hold the cam sprocket on. I'm going to let that dry a little bit, then apply some Loctite, red Loctite. We're also going to bias the cam gear in such a way so that if those bolts should ever loosen up, that cam gear is in the right spot anyway. But with the Loctite, nothing's going to move. That's a good practice to do. So we're now cleaning the block in preparation for the cylinder heads. It's critical to strip away every trace of oil, grease, or old debris from the mating surfaces. A pristine surface is the only way to ensure the head gaskets achieve a permanent high-pressure seal. We follow the exact same process for the cylinder heads, double-checking the surfaces before carefully lowering the heads into position onto the block. Unlike many modern engines that use one-time stretch-to-yield fasteners, the original Buick 430 head bolts are reusable, provided they're in good condition. We're using a wire wheel to strip away any corrosion and ensure the threads are pristine. This is a critical step because dirty or rusty threads will create friction that leads to false torque readings, which can compromise the clamping force and lead to head gasket failure. Apply a thin coating of engine oil to the head bolt threads to lubricate them, but don't slather it on because excess oil will drip off and get between the head and the block, and that will compromise the head gasket. We're torquing down the heads in 3 steps following the tightening pattern described in our manual. Tightening in 3 steps prevents the head from distorting. The final torque we're using is 120 foot-pounds. So we started with about 50 foot-pounds, then went to 80, and then to the final 120, each time using the tightening sequence as described in the manual. Now that we have both cylinder heads bolted down and to the correct torque, we're going to now pump up our lifters. We are using hydraulic lifters. They need to be pumped up with oil prior to installing them because you don't want to start these up dry. Once they're primed up with oil, we're popping them in one at a time into the lifter bores. We're also going to make sure that the camshaft is lubed up again with some more moly because we want to make sure we have a good amount of lubrication and stuff for startup. So now we're cleaning the block in preparation for assembling the timing case. We want to make sure that the block is clean and free of any oil. Contaminants like oil can cause your gaskets to leak, so make sure you clean things really good. We're also applying some assembly lube to the timing chain and sprockets to make sure they have some lubricant on them for the first startup. We don't want moving parts dry during first startup. That is not good. So we installed a new crank seal to the new timing case. And we're using a new timing case because this is a known weak area for these Buick engines. The oil pump is actually part of the timing cover, and since this is all aluminum, they tend to wear over time. Using a timing cover that is nearly 60 years old is risky, so we decided to replace it. We're cleaning off the gasket surfaces again to make sure they're clean, and we don't like relying 100% on the gasket for proper seal, although it probably would be fine. But we always put a thin layer of gasket maker where the gasket goes just to make sure things seal up good and tight. So before we put the timing cover on, we're going to lube up the eccentric on the camshaft where the fuel pump actuating rod or lever rides, as well as put a little bit of moly lube on the gear that drives the distributor. Now we're torquing down the timing cover following the service manual pattern, and again we're using a stepped approach to torque everything down to their final values. Now that the timing cover is on, we're going to repeat the process of cleaning and applying gasket maker and gasket to the new water pump, and also torquing that down to its correct specifications in a stepped approach and following the recommended pattern for tightening as laid out in the manual. Now it's time to put our damper on the crankshaft. We take out the bolt that we had been using to help us spin the crank during assembly processes, and we also put a little bit of lube on the ID of the damper, so where it mates up with the crankshaft to help things slide on, because these fits are typically very tight, very snug, because it's a very close fit. You don't want that slopping around. And you also want to put a little bit of lube on the OD of the damper where it contacts the crankshaft seal. You don't want to install that dry. Could damage the seal. Everything works better with a little bit of lube. We are ready to put on our harmonic balancer, and we're looking up the torque for that. Harmonic balancer to crankshaft, we are looking at 200 foot-pounds minimum. Yeah, that's quite a bit. That's quite a bit holding that puppy on. Luckily we got a torque wrench that goes up to 250? 250. So we apply a little bit of engine oil to the threads of the crankshaft bolt. It holds the damper on. That's to make sure it's lubricated properly. Again, if it's dry, you may get false torque readings, so it's always good to have a little bit of lube on there. Now we're getting ready to torque the damper on, but I'm not happy with pushing down on the torque wrench. That engine is really heavy, and now we're going to be pushing another couple 100 pounds down on top of that. So I said, you know what, let's switch it around. Let's go around the other way and lift on it. That way we don't risk dropping the engine. Now we're getting ready to find true top dead center for our number one piston. To do this, you use a tool called the top dead center piston stop. It's a simple mechanical tool designed to physically block a piston's upward travel so you can find the exact center of its stroke. It's essentially a hollowed out spark plug with a long bolt or rod running through the center. Most are made of steel or aluminum, this one's brass, and some use plastic tips to prevent scratching the piston head. This is the most common type for amateur mechanics. It threads directly into the spark plug hole of your number one cylinder. There are other types, but this one will do just fine. Because we can't see the actual tops of the pistons because the cylinder heads are on, what we're also going to do to make sure we got things right is check cylinder number 6, because when piston number 1 is at top dead center, piston 6 on this engine is also at top dead center. It's not the same point in the combustion cycle, but that's okay, that doesn't matter. So what we're doing is we're taking our endoscope here, which is basically a camera with a flexible mount at the end so you can put it down into small tight areas and see what's happening. And we're going to watch for the top of the piston to come up near the top, and that will tell us that we're close to top dead center, which will also be top dead center for number 1. Then we'll rely on our top dead center tool for exact measurements. So here we are, we got the harmonic damper put on. I want you to pay attention to what we're seeing here. This mark here is one of the engravings on the harmonic damper from the factory. It's deeper and thicker than this mark. That is another mark from the on the harmonic balancer from the factory. So there were 2 marks. As our machinist pointed out in our episode 2, he saw this on the damper and said he doesn't know which one's right. And there's no way to tell until you get the damper on the motor. So it turns out neither of them is correct. What we had to do was get a piston stop for number 1, and this mark here and this mark down here are the extremes of the piston travel. So halfway between those is this mark. That is true top dead center. And we have it now lined up with the 0 on our timing case cover, so we know that is correct. What we're going to do is take this masking tape off of here. We have a degree timing sticker coming in for this balancer, and we'll put that on. But in the meantime, we've put a little bit of a dimple in there with a sharp punch, as well as on the face, so that we don't lose this mark anymore. But this really stresses the importance of you cannot trust parts anymore, even from what was maybe a reputable company in the past. If things are made overseas, sorry, China, but you know, this is what you get. It's not right. You have to double check everything. This could have caused us some major problems had we just assumed everything was correct. So be forewarned. So here's a short description of how to use a top dead center tool. Pull all your plugs out in case they're not. Thread the top dead center tool into spark plug hole number 1. Hand tight's good, but we like to snug it up just a little bit. Carefully rotate the crank counterclockwise by hand using a wrench until it touches the tool. Go slow and feel for it. Stop immediately and mark the pulley or the damper exactly at the pointer where the 0 mark is. Now spin it the other way, all the way back around until it hits the tool again. I say hit, but don't hit the tool until you bump up against the tool. Make a second mark at the 0 pointer. Measure between those 2 lines with a tape measure. The dead center between them is your true top dead center. Take the tool out now, don't forget. Then just rotate your center mark to the pointer and you're all set. So as is the case on many American V8s, there are 2 dowel pins that act as locating guides for the intake manifold. And on this engine, the rear dowel is damaged. Looks like somebody smacked it pretty good. It's deformed. And what that means is the intake manifold mating hole will probably not fit very well. So what we're going to do is clean that off. We're going to obviously protect the engine from filings getting into the valley pan. But we're going to file that down, make sure it's round, smooth, the right diameter. Otherwise, the intake manifold won't go on. To determine the correct pushrod length, you'll need an adjustable pushrod tool like this one from T8 Performance. This tool features a threaded body that allows you to precisely dial in the length. What you want to do is set the camshaft, so rotate the engine until the camshaft is on its base circle, fully closed, for the specific valve you're measuring. Place the adjustable pushrod into the block, ensuring it is seated correctly into the lifter. Assemble the rocker arm assembly over the pushrod and torque the mounting bolts to factory specs. Lengthen the tool or shorten it until all vertical up and down play is eliminated between the lifter and the rocker arm. You have now reached 0 lash, when you can still rotate the pushrod with your fingers and feel a slight drag, but there's absolutely no vertical movement. Carefully tighten the jam nuts on the tool, but be careful, the threaded ends often want to spin as you tighten them. If the length shifts even slightly, you must start the process over to ensure accuracy. Carefully disassemble the rocker arm and retrieve the pushrod. Then measure its total length with a high-quality caliper. Document the exact measurement for that specific valve. Because Buick valvetrains can vary slightly across different cylinders, keep meticulous records is vital in order to avoid mixing up your numbers.
Due to the machine work, altering the height of the deck and the heads and a new camshaft, we can't use the stock push rods. So we measured what lengths we need, and over here on this chart, we have our intake and our exhaust. What the push rod length is at 0 lash, and we're targeting 40 thousandths to 60 thousandths preload. And we needed custom length push rods for almost all the intakes and one of the exhaust, and found some milling push rods that would work with the rest of them. Now they look, if we look over here, they look a little bit different, but these are the custom length ones. These are the milling ones I got off the Summit.
Explain some of the challenges we had with online data.
Yeah, the measurements weren't quite right. And when it comes to push rods, 3/8 and 5/16 sometimes is not 3/8 and 5/16 in terms of diameter and ball end tip. I had to take a few back. It's easiest if you just stick to a stock rebuild and a stock cam, but you can't really do that. You have to measure to make sure these are the proper length, and don't trust what they say, even from the manufacturer. On some sites, it was all wrong measurements, wrong length. So
yeah, wrong ball diameters, everything is suspect. You have to double check everything yourself.
For the 430, it oils differently than the 455. And we need non-oiling push rods because the 430 accomplishes its oiling through passages in the block and into the head that pressurizes the rocker shaft and then drips down to the lifter. The 455 is different. And I did not want to use a hybrid adjustable push rod. I'd rather use a one-piece. So this is what we've got to work with here. So let's get measuring and see if these will work, and we can finally button up the top end of the valve train.
So I guess to summarize, because of the differences in the heights of all these push rod lengths, we were not able to utilize one stock length, right? We have several lengths that we had to use just because, again, there's Chevy valves in these heads. They open up the breathing a bit more. And we're just not entirely sure if perhaps the valves are not all seated consistently height-wise, where the machining, where the seats are. We just don't really understand where the discrepancies are coming from, other than there are some. So we had to do a little bit of, actually quite a lot of research on lifter lash, lifter plunger travel. We tried to use AI tools to help us out, but that didn't work too good. We had to really come up with our own numbers. And yes, we know 20 to 30 is the ideal lash, but in this case, we have to go with something a little bit bigger. Turns out the lash on these, or I should say the piston plunger travel on these lifters is 120 thousandths. Is that right? I believe that's correct. So from the point where that lifter is fully up against its retaining clip, pushed all the way down, those plungers travel 120 thousandths. We wanted to stay away from the very top of the plunger travel and the very bottom of the plunger travel. So that's why we focused on the lash settings that we did. That gives us quite a bit of clearance at the bottom and quite a bit of clearance at the top, and it helped us reduce the number of custom push rod lengths required. So this is the best scenario we could come up with, and we're confident it will work. So now we're measuring all the push rod lengths that we got. And remember, there's a variety of different lengths for the situations that we have here. So we want to make sure, first of all, that they're correct, that they're what we ordered. And if they are, we're going to write down the exact length on those push rods, and then compare that to the spreadsheet that we have, which shows which length push rod needs to go in which position. In other words, Pushrod number 1 may have to be the exhaust valve for cylinder number 3. That's how specific things have gotten in this particular engine build. But, you know, that's what we got to do. So, again, we're being very careful about how we're doing this, and we're making sure that we're getting the right pushrod in the right location. Once we have all the pushrods in their right places, we are putting on the rocker arm shaft assemblies for both sides, lubing up everything again as we go, and torquing them down to factory specs. Once the rocker arms are on, we want to give the engine a rotation or two, make sure everything feels good, there's no binding. We double check each of the pushrods to make sure there's nothing loose and flopping around. And again, don't forget to take that top dead center piston stop out before you do any kind of engine rotation. Now we're going to take off our temporary masking tape, which helped us determine top dead center, and clean off that damper nice and clean and put our beautiful new degreed sticker on there. We want to make sure that we line up the 0 ticker on that tape to the punch mark that we made on the damper.
Very good. So our new sticker's on there now. We got all sorts of markings on here. We'll be able to time this thing no problem. And we got the true 0 mark lined up with our dot. Perfect. Feel much better about that.
So, as is often the case with old cars, parts that have been joined together years or decades ago sometimes like to become one with each other, and they get seized in there pretty good. So here we are with our stock intake manifold, and there's a water temp sensor that just will not come out. We've struggled with this thing, and we've tried heating it up, tried a pipe wrench on there because the sensor itself is brass, it's very soft. The tool that goes on there just mangled it. Vice grips, you name it, it just wouldn't come off. So we had to eventually just cut the thing off and use a Dremel tool to carefully grind away the ID of the sensor, and that way we could collapse it a little bit and break it free and get it out of the manifold. Here I am doing something a little bit dangerous. I don't have any gloves on. I'm old school. I just don't wear gloves. I feel they're a pain in the neck and they just get in my way all the time. But I suffer the consequences quite often. I cut myself all the time. My son actually makes fun of me. He says, "Hey, let's see if that's sharp. Dad, run your finger across that and see if you get cut." Because I do that. So just be careful when you do this kind of stuff. Don't do what I'm doing here. Wear some gloves or be careful because you could easily get cut on this sharp stuff.
Alright folks, well I finally got that stubborn sensor out of the intake manifold, but when I was using the Dremel tool, I did exactly what I didn't want to do. As you can see here, right there, I dug into the threads of the manifold. Great job. I think it'll be okay still. We'll put some gasket maker, ultra gasket black in there that's supposedly good for coolant and pressure, high temp situations. I think we'll be okay because we really want to use this manifold over again. But I tell you folks, don't get old because your eyesight, man, whatever.
So we've cleaned off the intake manifold. We've sanded off all the loose rust, flaky old paint, cleaned it up real good, degreased it. Now we're giving it a few coats of that gray cast iron look, which is good for high temps. Now we're getting ready to put the intake manifold on. And as before, anytime you have a gasket surface or a joining surface between parts, always clean it off really good with a good quality cleaner. Make sure you don't leave any lint behind, because it's important for the gaskets to have a clean surface in order to seal properly. And I don't know about all you folks, but man, I tell you, I can't tell you how many intake manifold leaks I've had in the past. Of course, that was on old Cadillac engines, 472s and 500s, but man, those things with the steel valley pans, they just did not like sealing up properly. So this has a nice set of gaskets. Hopefully we don't have an intake manifold problem with this one. Very important to use a good quality gasket sealer in those four corners where the intake manifold rests on those two rubber strips. Those two rubber strips there, each end, it's very important to put a good little glob of gasket sealer underneath those strips and on top of those strips so that those corners seal up when that manifold is in place. Now I'm marking the intake manifold gaskets with the sequential number of how the bolts should be tightened. Again, there's a pattern to this, and you need to follow that pattern to prevent distortion and warping, which will cause intake manifold leaks. Also, we're going to torque these bolts down in a stepped sequence as well to their final torque. Time to put the thermostat housing on the intake manifold. So the exhaust manifolds on this Buick are actually kind of interesting. You might hear about when Buick enthusiasts speak of pseudo headers on the 430 Big Block, which was produced from 67 to 69. What they're doing is referring to the factory cast iron exhaust manifolds, which were remarkably advanced for their time. Unlike the restrictive log-style manifolds found on many other engines of the era, Buick's engineers designed these to mimic the flow characteristics of a tuned header, while maintaining the durability and quiet operation of cast iron. The 430 engine and its sibling, the 400, was part of a $50 million engine redesign to replace the aging nailhead engine from the years before. The exhaust manifolds were a focal point of this performance-oriented engineering. The runners have a swept-back shape that curves towards the collector. This design reduces back pressure and utilizes the scavenging effect, where the exit of one exhaust pulse helps pull the next one out, similar to how a tubular header functions. The exit points where the runners meet were significantly larger and more streamlined than those of Chevrolet or Oldsmobile engines of the same displacement. Now, as you can see, these headers are obviously pretty old, and they're rusted at the interface surface between them and the cylinder heads. Now, some of the areas are pitted pretty deeply, and that's causing us a little bit of concern. We suspect that there's going to be some exhaust manifold leaks there. So what we're going to do is clean off and remove all this scaling and rusting and pitting, try to clean that off as good as we can. What we're going to do is use a JB Weld product called Extreme Heat Epoxy. What we're planning on doing is filling in these voids and deep recesses with the epoxy, then filing the surface flat and smooth again so that there's no areas for exhaust gases to leak out. We hope that'll work. This product is supposed to be rated up to 1,000 degrees Fahrenheit. It's possible that exhaust gases can reach higher than that, but that's usually when you're really stepping on the thing. And we don't plan to do that with this car because it's going to be a stock silent beauty. Hopefully this will work. Because these pseudo headers flow so well, many Buick owners choose to keep them even when modified. On a stock or mildly built 430, switching to aftermarket long tube headers typically yields only a gain of 10 to 15 horsepower, which many enthusiasts feel isn't worth the trade-off in heat, noise, and constant bolt tightening. So if you're lucky enough to have a set of these, hang on to them because they perform really well, they're stock, and they're a great alternative to tubular headers. So now that the manifolds are clean and prepped, I was ready to put the JB Weld Extreme Heat product onto those pitted surfaces. I had this jar laying around for a while, not sure how long. It was brand new, still sealed, as you can see, but as soon as I opened it, I could tell something was not quite right. It was very watery looking on top, and I've used this in the past, and it didn't look like that before. And when I started mixing it up, I thought, feels very hard, very clumpy. Didn't feel right, and no matter how long I mixed it, it just wouldn't get to the right consistency. It felt like wet sand. It's supposed to be a thick paste, so it didn't work out. It must have been laying around for too long, so I decided, you know what, I'm just going to chuck this. I'll order a new jar, and I'll keep working on it until that gets in. And as typically the case with exhaust manifolds this old, the studs have broken off, and you can't get them out. So we're going to have to go through the painful process of drilling them out and retapping these threads. So we finally got the broken studs out and rechased those threads. We're ready for new studs, and now our new JB Weld Extreme Heat has shown up, and we'll apply that to the exhaust manifold pitted areas. Okay, so we got the fanged surfaces of the exhaust manifolds covered in the JB Weld Extreme Heat. We'll let that dry, and then we'll file it down carefully, smoothly, so that we got some nice, smooth, flush surfaces with the divots, pockets, and any missing material filled in. I think that will work just fine. Another reason we're filling in these low spots and divots is because these exhaust manifolds are intended to be used without gaskets. It's basically metal on metal to the head. I don't really like that. I know that's stock, but I'm very used to having gaskets in there. And with the fact that there's low areas, I think gaskets would help seal this up. Once the JB Weld Extreme Heat had a sufficient amount of time to cure and dry rock hard, we carefully sanded off the excess, blending the original surface of the exhaust manifold with the extreme heat so that we had one nice continuous surface. We didn't take off any metal, or hardly any metal, on the exhaust manifold. We just wanted to knock down the high spots on the extreme heat so that it would match up with the original surface of the exhaust meeting surfaces. With the exhaust manifolds prepped and cleaned, we're applying a high temperature paint that creates the authentic look of fresh cast iron. It's a great color for this project and holds up perfectly to the heat. If you're looking for any of the products that we're using today, you can find them linked to Amazon in the description box below. Using those links is a fantastic way to help support our channel. We receive a small commission at no extra cost to you, which helps us keep these videos coming. We truly appreciate the support and thank you for watching. Now the manifolds are painted and cured, it's time to put them on. Again, we're using gaskets even though the stock situation calls for none. Not a fan of that, so we're going to use some gaskets here to help take up any voids or pits or anything that might be left over from our JB Weld experiment here. But we got to be careful when we torque these things down. These are cast iron manifolds, which means they're very brittle. Don't want to go crazy torquing these guys down because the gasket material is compliant, it's pretty soft. We don't want to impart any excessive loads to the ears of those manifolds because it could crack breaking off, which is not a good situation. We don't want that to happen at all. So we're going to be very careful about tightening these things down. Also, you'll see that we ran into a little bit of trouble with some of the mating threads for the exhaust manifold bolts. They were a little bit dirty, a little bit chewed up. Something was, I don't know, some crud down in there. We had to chase a couple of those holes with some taps of the right size. Again, make sure you don't get any of that debris falling into the engine. That's a bad situation. So we cleaned out those threads and then the bolts went in just fine. Well, we've made some great progress in this episode. The heads are torqued, the cam is degreed, and the manifolds and timing cover buttoned up. This build is finally looking like an engine. We also locked in top dead center, and everything is primed for the oil system and a fresh coat of paint in our next episode. But, as has been the case with this build, we ran into yet another hurdle, an oil pan with bolt holes that just wouldn't line up. We thought that frustration would be our biggest problem, but then the unthinkable happened. Alright, folks, slight catastrophe here. Nobody got hurt, but look what happened here. This engine just tipped when we rotated it to paint it. It hit the floor pretty hard. We hope we haven't damaged anything. Hopefully heads are okay. I'm seeing a piece already right there. Really? Good God. Alright, well, we're going to have to get the hoist out. We're going to have to lift this puppy up and see what the hell's going on. What is that? What do you think that is? Well, it looks cast iron. I don't know. And, of course, paint in the valve train. Oh, man. My God. Well, there's obviously cracked parts. Who knows what happened here? Is the block cracked? Did we lose the crank? What else? It's sitting on the rocker arms, so that ain't good. We really don't know if there's going to be a next episode anymore. This project has been one challenge after the other. This could be the breaking point. How about you hit subscribe and stay tuned, folks, because we're about to find out how much of this engine is left to save.